Hello, everyone. So today we're going to end up talking about a device that is really quite useful um, called a transformer. Not the kind that goes from car to robot, different kind of transformer. So transformers, they have three basic sort of pieces to them. You have a primary coil, you have a secondary coil, and then you have a sort of a linkage between the two. They're insulated from one another, but there's a linkage between the two in the form of a piece of iron. And when it's in this configuration, this piece of iron is called a yoke. So I have this attached to a DC source, which is not really the way um, transformers are normally used. I'm doing it this way because it allows me to zero in on very select points in time to talk about what's happening at those points in time. Once you get the general idea for what's going on, I'll talk a little bit about how they act in AC systems. And in any case, I'm going to call the number of wines in the primary N sub P and the number of wines in the secondary N sub S. So at T equal to 0, I'm going to throw the switch. Current's going to start to flow in the primary. It turns out that a bunch of stuff is going to end up happening, which we will talk about later. But just suffice it to say that you're going to end up having a magnetic field set up down this axis. And because this is iron, the domains are going to end up flipping into alignment, and that magnetic field is going to extend all the way around, and it's going to go through the secondary coil. And as that magnetic field builds up in the secondary coil, you're going to get a changing magnetic flux through here. And that changing magnetic flux is going to induce an EMF, which is going to induce a current. So while the magnetic field is building up, you're going to get current in the secondary coil, which means you have transferred power from the primary coil, the primary circuit, to the secondary circuit. This transfer, this current in the secondary will only last as long as the magnetic field is increasing through the primary. So as soon as it goes to steady state, as soon as the current through here becomes steady state, and the magnetic field down the axis ends up being constant, then you will no longer get a current in the secondary. Now, as I said, there's stuff that goes on in the primary as the current is building up. The current doesn't build up immediately, and the reason why is because you have a changing magnetic flux through the primary coil, and it's producing its own EMF, which is trying to produce its own induced current, which is fighting what is going on. And what is going on is that it's trying to increase the magnetic field on the axis. So it's trying to slow that increase, because that's what Faraday's law and induced EMFs do. They oppose the change. That's what Lenz's law was all about. Was talking about how the induced EMF and the induced current is fighting the change that produces the effect. And so here the current is increasing. It's not going to increase as fast as it would have because of the magnetic induction interaction. That's all kind of a side issue here. What we're really, and I'm mentioning it only because I'm letting you know that this magnetic field is increasing. It's increasing fairly slowly in comparison to what it would have been doing if that magnetic induction phenomena hadn't been occurring. Having said that, though, what we're really interested in is what's going on over here. So after a period of time, the switch gets opened. And when that happens, this current dies out. And again, it doesn't die out quite as fast as it normally would have, because now the magnetic flux is decreasing, which means you get an induced EMF that fights the change, etc. But again, what we're really interested in is what's going on over here, because over here, now the magnetic field starts to diminish. And as it's diminishing, the magnetic flux, it produces an induced EMF, which produces an induced current. happens to be opposite the direction that we had before. But in any case, you get current through the secondary. So once again, you've transferred power from the primary to the secondary as the magnetic flux is changing. Okay. Once you go to steady state, no more current. So if you were to go ahead and graph all of this, what you would have, if you're looking at the magnetic field through the secondary, is when there's no magnetic change, you get no induced EMF. As soon as there's a change, you get an EMF and a current. No change, no current. You get a change, EMF and a current. Okay, so that's generally how transformers work. As long as you have a changing magnetic flux through the secondary, you're going to get a current in the secondary. What about the math? Well, we can write out what the EMFs are in the secondary and the primary. And then we can take the ratio of the two, because notice the change in flux with time is going to be the same for both the primary and the secondary. So if we take the ratio and we cancel those out, we get this relationship that identifies what's happening with this secondary EMF to its primary and the Wiens ratio. And they're proportional to one another. Okay, that means if you have more Wiens in the secondary than you do in the primary, the EMF in the secondary is going to be bigger than it was in the primary. Which means if you have more Wiens in the secondary, you're basically going to be stepping the voltage in the secondary up relative to what it was in the primary. Okay, that particular kind of transformer is called a step-up transformer. And again, we're looking at a DC setting. When we talk about an AC setting here shortly, you'll see why this is kind of advantageous. If the number of Wiens is in the secondary is less, you'll end up with what's called a step-down transformer. Now, what about current? And, well, what about current? What's really being transferred is power. You're transferring power from here to here. And so if you write out the power relationship, this is essentially V times I. The EMF is equal to this. You do the math, and you come up with this relationship that says the number of Wiens in the secondary to primary is equal to the current in the primary to secondary. They're inversely related. And so kind of the bottom line of the whole thing is if the voltage goes up in a step-up transformer, the current is going to go down. Minor point, whether it's a step up or step down is governed by what the voltage is doing. Okay, so if the voltage in the secondary is going up, it's a step-up transformer. If the voltage in the secondary is going down, it's a step-down transformer. Okay, so again, doing this with a DC source is really kind of dumb, because the only time you're going to get any action over here is when you're making the voltage change. In an AC situation, the voltage is constantly changing. Okay, so this is the high voltage side, and then this is the high voltage side, and then this is the high voltage side, and then this is the high voltage side. And if you were to graph the polarity across here, it would actually look like a sine wave. Okay, which is the reason why the symbol for an AC source looks like a circle with a sine wave in it. So, what are these things useful for? Well, the motherboard on a computer could require anywhere from 2 to 5 volts. Your wall socket provides 120 volts. Okay, so you can't very well just plug a computer straight into a wall socket, because it would just blow it out. So what they do is the 120 volts gets plugged into a transformer, a step-down transformer. The Wiens ratio is such that if you have 120 volts across here, you have maybe 5 volts across here, and then this is the part that ends up going into the computer proper. And in fact, if you were to take a computer and open it up, you would see that the cord would come into the computer, and the first thing that it would go into would be a transformer. It would be this kind of a bulbous looking thing. And if you looked at it closely, you would realize it was Wiens of coil around some kind of yoke. Minor point, the symbol for a transformer looks like this, and you can't see it very well because the picture is in the way, but I'm afraid if I get rid of the picture, I won't know how to get it back, and Lord knows it would be tragic if you wouldn't be able to have a chance to see me. So I'm just going to allow you to take a look at the PowerPoints to see basically what the transformer symbol is. This is a coil, so it's like a coil. And this is a coil, so it's like a coil. And they're not electrically connected, but the three lines in between are supposed to suggest that there's a magnetic coupling between the two. So how might you run into a problem, or what kind of problem might you run into? You go off to Europe, say you go to France, and the wall sockets there are 220 volt or 240 volts. And you take your favorite hair dryer or razor or whatever, and it requires 120 volts. And so you would have to go, someplace and buy a converter. And basically, what the converter would be a transformer. What kind of transformer would you need? Well, you need to have 120 coming out. If a 240 goes in, that is a step-down transformer. Now, minor point, and this is definitely a side issue, especially for the AP folks, because you are not going to have to worry about AC on the AP test. But I'm going to tell you about this anyway because it's interesting and it's something you ought to know about. You're told that the wall sockets are 120 volts AC. What does that mean? What does that mean? So the deal is this. AC, because the power supply has its voltage flipping back and forth, it means the charge carriers are feeling an electric field that are making them go in one direction and then the other, and then the one direction and then the other. And because current is defined as the amount, technically in a DC setting, current is defined as the amount of charge that passes by a particular point per unit time. In an AC setting, that definition kind of goes out the window because the amount of charge that passes by this point in a unit time over a period of time is zero. Okay, the charge is going this way as much as it's going that way. So effectively, from a DC perspective, the net effective current flow is zero. And so the question is, if you put an ammeter in the circuit, what's it going to read? And the answer is, it will read the DC equivalent current for the circuit. It will tell you how big the DC current would have to be to provide the same amount of as the AC power supply is providing. Now, it turns out that value is 0.707 of the maximum current in the circuit. So if the current's acting like a sine wave, there are times when there's no current, there are times when it's maximum, then there's maximum going the other way, etc. If you take the maximum current that flows, and you take 0.707, and I'm not showing you the math, but this is what the math, this is where it comes out to be. If you take the square root of the mean of the square of the current, and the reason you're doing that is because the square of the current is related to power, I squared R, and that's what you're interested in, is power. If you take the root mean square and calculate it, you will come up with this effective current, this DC effective current, and it will equal 0.707 of the amplitude of the current value. That's referred to, I think they ought to call it the DC equivalent current, but they call it the RMS current. Okay. By the same token, similar kind of thing with voltage. The voltage across here, if you put a voltmeter across here, what's it going to measure? Okay, it's going to give you a single value. What's that value going to be? It's going to be the value of the DC source that would provide the same amount of power to the circuit that the AC source is providing. And that's also going to end up equaling 0.707 of the amplitude of the sine wave. Okay, so Your wall socket, if you plug a voltmeter into your wall socket, it'll tell you 120 volts. That's the RMS value for the wall socket, which means if you fuss with the math, that the maximum voltage that that wall socket will generate, the maximum voltage difference between the two plugs, the two terminals, is about 170 volts. So as an extended bit of amusement, the wall socket is oscillating at 60 cycles. If you put all of that into this relationship, you end up with an amplitude of 170, and the argument for the sine turns out to be 377. You put in 60 here, which means that if you ever see a schematic in which they say that the power supply is 170 sine of 377t, you know that basically what they're doing is they're telling you that this power supply is just being plugged into the wall. Anyway, with all of that information, we're back at the ranch with our, going off to France or wherever. What's the wines ratio going to be for this thing? You just use your little relationship. You know that the secondary's got to be 120 and the primary 240. So the wines ratio is going to be 1 to 2. If you wanted to know what the current had to be, if you knew that the secondary had to be 3 amps because that's what what was required to make your dryer work, once again, you could go ahead and use your relationship, put in the information that you knew, and you could come out with what the current would be. So this is an example of a problem with using the math associated with a transformer. The other thing that I wanted to talk to you about, and I will make this fairly quick because I know that this is lengthening out, has to do with power production, like at a power plant. And we've talked about this to some degree, but there's an added twist to it that has to do with transformers. So what we've said about power is you have a turbine, something blows across the turbine. If it's hydroelectric, it's water. If it's nuclear or coal, it's steam. But somehow or other, the turbine gets rotated, it's attached to a shaft, there's a coil, magnetic field, coil rotating in a magnetic field is going to produce alternating current across or alternating voltage across its leads. So the problem though, and you can actually figure out, if you write out the expression for flux, take the derivative, you can figure out what the EMF, what that voltage is going to be. And lo and behold, it's a sine function. This is exactly what we said it should be for AC. The problem, though, is that you need to be able to get this from the power supply or from the hydroelectric dam to the city. And that means you're going to have to transfer it via wires a long distance, and you need to diminish power loss. And so how do you do that? Well, it turns out that power loss is mainly generated by high currents. So what they do, cleverly, is they take the power that's being generated by the rotating coil and they put it through a step-up transformer. And it shoots the voltage up to like 50,000 volts. That's the high tension lines that you see around. But in doing so, it drops the current down to practically nothing because that's what happens in step-up transformers. Voltage goes up, the current goes down. And so they have practically no energy loss as they transfer the power from the power supply to the city. Now, once they get to the city, they go ahead and they put what's come in through a step-down transformer because, toasters can't handle 50,000 volts. And that pushes the current up. And so, lo and behold, you end up with, the ability to power lots and lots of toasters out there with 120 or 240 volts. It turns out, interestingly, that the last little bit of amusement that I will tell you before I let you go, Edison wanted to power the country with DC. And Tesla, who was just a little nobody, but brilliant, finally got the backing of a guy named Westinghouse, and he wanted to use AC. And the downside of using DC is that you needed chemicals to be able to generate the DC, and it didn't travel very well. It died out pretty quickly, so you couldn't just make it someplace and then send it 200 miles. And so if we had done DC, we would have power generating stations every mile or so, literally all across the country. What Tesla basically said was that AC was really ideal because number one, it's really easy to produce. You just take a coil and spin it in a magnetic field. But what was really nice about it was that you could transfer it really long distances without losing the power. And the reason why was because you could put it through a transformer. You could step the voltage up and the current down with a step up transformer, and then once you got to the city, you could step the voltage down and the current up with the step down transformer. So anyway, fortunately, Tesla and Westinghouse won out. It's one of those rare instances when Congress, well, actually, I shouldn't say that. We'll just say that Congress acted reasonably, and we ended up with AC being the norm, and thank God they did. And so, anyway, that's pretty much all I have to say. So that's it. Have a nice day.